Okay, I'm going to just hit some highlights here, give you a basic idea of electricity, and I'll try to give you some pointers on how to finish up that worksheet as well. Electricity is a lot stronger than gravity. If you saw Brian Greene's An Elegant Universe, he has somebody falling toward the pavement, and they land on the pavement with their feet, and he says, well, that was gravitational pull, so why didn't the person keep going to the center of the earth? And the question, or the answer, of course, is that there was pavement, but the specific answer is that the electrons on their feet repelled the electrons in the pavement. And so that electron repulsion was enough to stop gravity cold. We know about electrons and protons. You can gather up a lot more electrons if you put a sweater on, or rub your feet or something like that. You're going to gather up those electrons and shock somebody. Those can be discharged. What's kind of interesting here is that Newton's law of gravitation, which we have looked at before, where we have mass 1 and mass 2, and for like our F sub g, we said this was the Earth and this was our mass. The g was a constant, and this was the distance between the center of the Earth and us, basically the radius of the Earth. And we could do that with anything. Coulomb's law. Coulomb's law looks exactly the same. The k, though, is going to be 9 times 10 to the 9th. Charge 1, charge 2, if they're a positive and a negative charge, of course they'll attract. That's the force of attraction. And if it's a positive and a negative, that's the attraction. Or if they're both positives or both negatives, that would be the force of repulsion. And this is the distance between them squared. So kind of cool. The Coulomb of charge we're going to look at, and definitely jot this number down. A Coulomb of charge is 6.25 times 10 to the 18th electrons. Those negative charges. And it's kind of interesting to plug numbers into this equation. You're going to get these giant numbers, but a net charge like that doesn't exist. There are charges everywhere that are going to repel and attract that charge. And this is just an example if you were to put similar kind of numbers into F sub g. So you find that gravity is much less of a force than electricity. Conductors and insulators, I don't think we're going to spend a lot of time on that. Obviously, conductors are things like copper wire is a great conductor. And semiconductors, we are used to talking about those, but what's kind of cool are superconductors that actually have infinite conductivity at close to absolute zero. We talked about getting charging by induction. Thunderstorms, interestingly, have the bottom of the clouds are negatively charged, and they induce a positive charge on the surface of the Earth below. And the discharge of those electrons is where we get lightning. These lightning rods that Ben Franklin devised to kind of discourage fires starting from a buildup of charges or a discharge of charges. Let's see, electric fields and potential. We're not going to spend a lot of time with electric field, but just to kind of give you an idea of what I'm talking about, if I have an electric field like so, I drop a positive charge into that field. Well, what's happening with that field? Well, basically what it's going to be is what would happen if you put a positive charge in there. And a positive charge would repel the other positive, and it would go toward or attract the negative. So that's an electric field. And do more with that later. We obviously could apply a direction in a magnet. Here's an example of some electric fields, some pictures or schematics of electric fields. Now, we're not going to talk about shielding. Electric potential energy. So if you go back to that idea of, I have this electric field and got something going there. If I throw a positive charge in there, the reason that these lines are going this way is because we talk about electric fields is how does it act on a positive charge. Would you agree that if I take that positive charge and I push it over here, I'm pushing it over this way, that's going to take some work because it's repelled by those. Two positives are repelled by each other. So if I push this one this way, I'm actually giving it some potential energy, and I let it go and it will accelerate toward the negative with some energy of movement, kinetic energy. And of course, the closer we push, the more energy we have to overcome that repulsion, but now we have more potential energy. We measure electric potential in volts, which we'll get to in a second, but that is electric potential energy in joules over coulombs of charge. And that's going to be our voltage. And I think the next slide actually shows that. Yep. So the volts or potential energy voltage is a joule over a coulomb. So you don't need to know that. If a conductor has a potential of 1,000 volts, what they're saying is it would take 1,000 joules of energy per coulomb of charge to bring the charge from far away and add it to the conductor. So how much energy to add the charge of one proton to this conductor? Well, if I have 1,000 joules per coulomb, and I have 1.6 times 10 to the negative 19 coulombs of charge, then when we multiply that, it'd be 1.6 times 10 to the negative 16 joules of energy that's going to be required. And we're not talking about a lot of charge here. Just remember what a coulomb is made up of electrons, electron-wise. Okay, now this is a ratio of energy to charge. So basically that comes down to is high voltage is only a problem if there's high charge. Now, if you see a high voltage charge signage that says danger high voltage, there's a lot of charge there too. An example would be like sparklers. Those get to be 1,000 degrees Fahrenheit. So why do we let little children play with them? Because they're just a tiniest little bit of that high temperature. So even if it hits your skin, probably hurts a little bit, but it's just such a little amount at that energy. Okay, all of that. Electrical storage are capacitors, and they're found in all of our electronic kits. They're pretty simple, obviously, and they look a little bit like this, but of course they can be gigantic as well, depending on how much you want to store. These do have polarity. You're going to have a long end and a short end, and they're going to correspond to the positive and negative charges. So when you're doing your electric kits, be careful with those. They do have polarity. They do have to go in the right way. Capacitance, we can calculate with charge over voltage. And so the units there are going to be farads. And, oh, I didn't write in that example. So let's just do an example here of 5 microfarad capacitor. And we're going to connect that to a 12-volt battery. What charge on each plate? Okay, and that could be a little q too. So we're going to go 5 times 10 to the negative 6 farads. Okay, I want to get that out of microfarads. Is going to equal Q over 12 volts. And so the charge, 6 times 10 to the negative 5 coulombs of charge. Discharging a capacitor with our little electric kits, not a big deal, but they're going to have those little paper wrapped up between, and that's going to be the conducting path. But if you're it and you're between the discharging of the capacitor, positive and negatives, it could be shocking or even fatal. The older TVs, they said even if the TV is unplugged, do not take this apart because of the capacitance in that TV. So I don't know if that's the newer TVs now, but the older ones, they said don't take this apart even if it's unplugged. Okay, another example. Okay, flow of charge. We're going to talk about electric current. Potential energy means a flow. So we could do a brief flow before coming to common potential, or we could do a sustained flow. Because you're going to, just like the second law of thermodynamics, if you have high temperature to low temperature, high charge to low charge. Now it depends on the substance, how it carries that charge. In metals, the electrons are very free to move around, and so they're really good conductors. This is measured in amps. Conductance, or current, is measured in amps, and the flow of 1 coulomb of charge per second. And again, remember, that a coulomb is 6.25 times 10 to the 18th power electrons. So in a wire that carries a current of 5 amps, 5 coulombs of charge pass across a cross-sectional area of the wire per second. Okay, so just doing an example here. The standard international unit of amps, it's coulombs of charge over time. So 1.67 coulombs of charge pass through a filament in 2 seconds. What is the current? Take 1.67 coulombs per 2 seconds, 0.835 amps. Okay, obviously your voltage sources, batteries, dry cells, wet cells. We are not going to look at the electro. Skip that. All right, electrical resistance. We sometimes want this resistance because you don't want that current to just happen and be over quickly. You want to have, or it could overheat. You want to have some. Depending on the material, it's going to be a better conductor, a better resistor. You have to ask how thick is the wire. Resistance is less in thick wires. How long is the wire? Longer means more resistance. Obviously, it's got to travel farther. And the temperature. Increased movement of atoms means more resistance just because physically more interference. So here's some examples of what's going to cause or help resistance. And this is what the resistors look like in your electric packets, your electricity packets. They do not have a positive or negative, so it doesn't matter how you put those in. Okay, to calculate it, and this is going to be the last thing in this thing, we're going to take Ohm's law. Current in a circuit is directly proportional to the voltage impressed across the circuit and inversely proportional to the resistance of the circuit. So the current is going to depend on the voltage and the resistance in ohms. So let's give it an example here. What is the resistance of a frying pan that draws 12 amps of current while connected to a 120 volt circuit? So I've got my current at 12 amps, my voltage 120 volts, and we're going to have resistance equal to voltage over current. So 120 volts divided by 12 amps, we get 10 ohms of resistance. So resistance is not futile, it's just current over voltage. All right, to finish up, electric shock really depends on the applied voltage and the resistance of your body. Dry, if you're completely dry, it might be up to 500,000 ohms. Wet, it could be as little as 100 ohms, depending how damp you are. Generally, you can resist quite a bit, about 100,000 ohms. So if you touch the 2 electrodes of a battery, 12 volts probably wouldn't feel, 24 volts. With your body of a resistance of about 100,000 ohms, here's where you'd feel it, and then where it actually becomes serious. So just as an example, say that your feet are a little damp, the floor is a little wet, your resistance is about 1,000 ohms, and you touch a 24 volt potential difference. With different hands, I got 0.024 amps going through your current, so that's not so good. 120 volt light fixture standing in the ground, resistance between your feet and the ground is probably enough for you to be okay, but if the ground is wet, okay. Birds on electric wire, okay, because there's no difference in potential, and if you were to fall, say you're on, working up there, and you fall and you hold on to the wire with both hands, you're okay, but the second you let go of it and touch something else like the pole, then there's a potential difference and you're in trouble. Okay, I think that is it.